Alright, in this session then we are going through mathematical transformations. So this is part of geometry and measures. So when we transform an object, it means that we're going to change its appearance using specific mathematical rules. And there are four that we need to be able to deal with: enlargement, translation, reflection and rotation. Now we're going to take those one at a time. The only one that will actually change the size of a shape is the enlargement. And even though in the English language enlargement generally means something's become bigger, in maths an enlargement can actually make something smaller too. So rather than talking about enlargement and reduction, we can talk about just enlargement but making something smaller. When something is translated, reflected or rotated, then how it looks on the page will change. So it could be in a different position, it could be turned so it's upside down or at 90 degrees, or it could have flipped if it's been reflected. And the transformation may contain more than one of those processes, so a shape could have had multiple transformations acted on it. As far as GCSE questions are concerned, we could give you, or you may find yourself given the original and the transformed shape, and you have to write what has happened to it. And then a bit more language. When transforming a shape, the original is called the object and the transformed shape is called the image. So you may see those words cropping up on an exam paper. So first of all then, let's take a look at enlargement. So in order to perform an enlargement, you need to be given some specific information. You need to be given a scale factor, how many times bigger or smaller the enlargement is going to become, and usually, but not always, be given a centre of enlargement. If the scale factor is larger than 1, the image will become larger. If the scale factor is between 0 and 1, so a scale factor of 1/2 for example, then the image will become smaller than the object. It is possible to perform an enlargement with a negative scale factor, but at intermediate tier we don't need to worry about that. So as long as we can handle positive scale factor greater than 1, which will make something bigger, or a positive scale factor between 0 and 1, which will perform a reduction. So let's take a look at what we need to do here. So enlarge the shape shown on the grid by a scale factor of 2. So let's see. So enlarge is the command word, and then the detail is scale factor of 2. So we're going to make this shape twice as large as it is now. Now, if they weren't giving you a centre of enlargement, that means you could copy that shape or enlarge that shape anywhere on that grid, and so long as it was exactly twice as large, then that would be twice as big, then that would be fine. But if they give you a centre of enlargement, which you have to enlarge it from, then what that will do is it means that every single person who does this will have the enlargement in exactly the same place. So that's why more often than not in an exam paper they will give you that centre of enlargement, because it makes it easier to mark. So this is how you deal with this. You count squares. You count across and up or down. So to go from the centre of enlargement, which is there, to that point there, which I've marked with a cross, you need to go across 3 spaces and up 1. So in the enlargement you need to double that. So rather than going across 3 and up 1, you're going to go across 6 from the centre, 1, 2, 3, 4, 5, 6, and up 2. So that point in the enlargement becomes there. Once you've got a starting point, you can now just enlarge the shape, but it's usually better just to keep going from the centre so that you remember that that's what you need to do. So if I put a circle around that one, to get from A to that point, I'm going across 2 and down 1. So in my enlargement, I'm going to go across 4, down 2. 3, 4, 1, 2. So that becomes there. Then if I put a square on that one, I'm going to go across 1, 2, 3, down 3. So in the enlargement, it'll be across 6 and down 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then the final, which I shall do with a little star, across 1, 2, 3, 4, down 1. So across 8, down 2. 1, 2, 3, 4, 6, 7, 8, 1, 2. So the cross ends up there, the star there, the circle there, and the square there. Once you've got your points, then you just join them together with done it wrong, haven't I? Well done, Jones. To the circle, not to there. Now you don't need to do stars, crosses, circles and squares. I'm just doing that so that it's easier for you to see what I've matched up. Okay, so that's basically what you need to know for an enlargement. So if we take a look at the second one, it'd be worth you now pausing and having a go at this yourself, and then coming back to see how you've done. So enlarge is the instruction. Scale factor 2, so it can be twice as big, using A as the center of the enlargement. So A now happens to be inside the shape, but what we do is going to be exactly the same. So if I put a circle around that point, across 1, up 1 will become across 2, up 2. If I put a plus on that one, it's going to be up and across 1, 1, 2, 2. If I look at this one here, which I'll do with a triangle, it's to the left 1, down 1. So it'll be to the left 2, down 2. So that gets a little bit confusing now because I've got another triangle there. Well, to get to that one, I'm going to the left 2, down 2. So that's going to become 1, 2, 3, 4. 1, 2, 3, 4. So that is going to end up there. Then I'm going to go down 2 to get to there. Then I'm going across 1, 2, 3, 4. So I'll be going across 1, 2, 3, 4, 5, 6, 7, 8. Then in 1, up 1 will become into up 2. And then I'll be going back to the start. So the shape that you should end up with looks like that. So what you note there is that I initially started off counting from the center out, but once I got down here it was easier then just to say, well, I've got the basic position of my shape, now I need to double all the sizes. So then we have enlarge. Triangle shown by a scale factor of 1/2, using the origin as the center of enlargement. So this hasn't printed very well as far as the grid is concerned. The origin is the center of enlargement. The origin is at the center of the axis. So I'm counting everything from there. So if I take this corner here, I'm going across 4 to the left and up 4. So a scale factor of 1/2 will halve that. So rather than going across 4, up 4, I'm going to go across 2, up 2. Then this distance is 2 squares, So in my enlargement, that will become 1 square. Here I'm going up 2, so that's going to now only be up 1, and it's 1 square in, so that will be half a square in. So the shape that you end up with is that one. Half the size and half the distance from the origin that the original was. And then the final example on enlargement is one where they're telling us to enlarge. They're giving us a scale factor which is 2 again, but this time there is no centre of enlargement. So with this one, you can draw it pretty much anywhere you want, so long as it fits on the page. So I've got, it's going across 2, so it's going to go 4, and down 1, 2, 3, 4, 5. So I need to have 10 squares down, 1, 2, so if I started there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it's going to go across 4, 1, 2, 3, 4. And then across from there 3 down 2 will become across 6 down 4. 1, 2, 3, 4, 5, 6, 3, 4. So there's your enlargement. So that time, when I was doing that in class, lots of students had it in different places. So long as it was twice as big, that was fine, but its position didn't matter. So that's enlargement. The next one we look at is translation. So when a translation, an object is translated, it's moved up, down, left, or right. In order to describe a transformation, the information is given as a displacement vector, which looks like this. So you've got a bracket with 2 numbers, one on top of the other, but not as a fraction. The top number tells you how far it's going to move horizontally, and the bottom number tells you how far it's going to move vertically. Positive numbers, just like on an axis, will be moving in that direction horizontally and up vertically, and negative would be the opposite. So to translate the rectangle below by 2, 4 means that I'm going to take that corner and I'm going to move it 2 squares horizontally and 4 squares vertically, both positive. 1, 2, 1, 2, 3, 4. So that corner ends up there. This corner, 1, 2, 1, 2, 3, 4 will end up there. This corner, 1, 2, 1, 2, 3, 4 will end up there, and then this corner, 1, 2, 1, 2, 3, 4 will end up there. So it's taken the shape, it hasn't changed its size, it's just changed its position on the grid. So pause, have a go at this yourself, come back. Translate the triangle shown below by 8 minus 2. So if I take the top, it's positive 8, so it's going to go across 8 squares. This hasn't copied very well either, but that's 5 to there, 6, 7, 8. So that's 8 across and then 2 down. So that will move to there. This will move 8 across, which will take it to it's minus 4 there, so that will be 4 and 2 down. And that one will be 8 across, so that will take me to 2 and 2 down. So So the whole shape doesn't change size, doesn't change orientation, just changes position. And with the translation, they like to stick an extra little mark on the bottom where it says describe the translation, which will reverse. So if I was going from there to there, how would I write a vector like that to do that? And all you need to do is reverse the signs. So we're going backwards. So we're going to go -8, 1, 2, 3, 4, 5, 6, 7, 8, up 2. So that's translation. Reflection. When an object has been reflected, sorry, mouthful of coffee. When an object has been reflected, the image faces in the opposite direction to the original. Just imagine if you stand in front of a mirror, the image is opposite to you. Every point on the original and the new image is the same perpendicular distance from the line of reflection. So again, if you think of a mirror, if you imagine you're in a changing room in a shop, you've got a full length mirror in front of you. If your nose is touching that mirror, then your reflection nose is also touching the mirror. If you step 2 paces back away from the mirror, your reflection is exactly 2 paces away from the mirror as well. So in order to be able to reflect, you need to have some specific information. You need to be told where the mirror line needs to be. It'll be a straight line, and the information is usually given to you as an equation linking x coordinates and y coordinates. If it's a vertical mirror, the line will be x equals the number. So it'll be x equals 4, x equals -2, x equals 0, or in the y-axis. And this is because if you've got, for example, x equals 4, if I use this up here, let's say x equals 6, the x coordinate 6 is there, and every point above and below that also has the x coordinate 6. So the line x equals 6 creates a vertical line going through the x coordinate 6. If we are given a y equals, like y equals 3, then the y coordinate 3 is there, and the y coordinate 3 is fixed as we move along there. So if I'm there, for example, the x coordinate is -2, the y coordinate is 3. If I'm here, the x coordinate is 6, but the y coordinate is still 3. And that confuses students, because for them the x-axis is horizontal, so x equals 3 should also be horizontal. So that's where students lose marks with this. And even in class, when I hammered this and said, look, you've really got to concentrate here, still students make that mistake. If they're being really horrible on an exam paper, they could ask you to do a reflection on a diagonal, and they might ask you for y equals x. Well, y equals x is where the y coordinate is always the same as the x coordinate. So for example, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on would plot along a diagonal line through the axis. And if they've been really monstrous, they could give you y equals -x, and that's a diagonal that runs in a downhill direction. So let's see how we deal with these. So the first one, reflect. Okay, so if they're asking me to reflect, they also need to tell me where the mirror is going. The mirror is going on the line x equals 1. So the first mark here is for drawing your mirror line in the right place. X equals 1. There's the x coordinate 1. Now, am I going to draw a horizontal? No, because here the x coordinate isn't 1 anymore, it's 2. X equals 1 all along this line. So that's the line x equals 1. That's my mirror. So this point here is 1 line away from the mirror. So the reflection will also be one line from the mirror. This corner is 1, 2, 3, 4. So its position will of the reflection will be for the other side of the mirror. 1, 2, 3, 4. And the box corner is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So once you've got your corners, then you can join them together. And there's your reflection. Okay, so you have got the next. Pause, come back. Reflect the rectangle in the line y equals 2. So y equals 2 goes through the y coordinate 2, so it has to go in this direction. This line is 1, 2, 3, 4 below the mirror, so it will become 1, 2, 3, 4 above the mirror. And then it's 3 high, which will take you to there. So there's the reflection. And usually you can check when you're looking at something that's symmetrical, the line of sight, the human brain likes to have symmetry lined up along the line of symmetry. So by turning that and looking along that line, you can see that if you folded that over, it would overlap in the same way with that one. So we've got one more reflection to look at, which is the horrible one. This time we're reflecting in the line y equals x. So the line y equals x, as I said, goes through 0, 0, 2, 2, 4, 4, so that's the line y equals x. Now this is horrible because the grid hasn't photocopied very nicely, but what you need to do with this is, if you remember what I said, that the reflection is perpendicular to the mirror. So perpendicular means at right angles too. So we can't now count horizontal distance. We've got to count the diagonals in the squares, because the diagonals are at right angles to the mirror. So if we take this point, that's going to be 1, 2, 3, 4 diagonals. So it's more confusing because of the grid underneath. So this will be much easier on the exam paper because the squares will be clear. So I'm going 4 diagonals. 1, 2, 3, 4. So that point ends up there. This point is 1, 2, 3, 4, 5 and a half diagonals. A half, 1, 2, 3, 4, 5. So that point ends up there. And then the plus is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So our reflected shape is like that. So all you need to remember is, if they ask you to reflect on the line y equals x, or the line y equals minus x, which would be going that way, then you count the diagonals to the mirror rather than straight lines, because it's the diagonals that are at right angles to the reflection. So that's reflection. Then we come to rotation. So when rotating an object, there's three pieces of information they need to tell you. They need to tell you how much to turn it, and usually that's given to you as an angle, 90, 180 or 270, but more often than not 90. Which direction they want you to turn, clockwise or anti-clockwise, and around which point you want the object to be rotated. And this is usually given to you as a coordinate or about the origin. And this is one of the few bits on a maths paper where a little bit of tracing paper is helpful and is something you will be provided in your exam. Lost where I am. Okay, rotate. So there's my command. I'm rotating. I need to know how much to turn, 90 degrees, which direction, clockwise, where am I pinning my rotation to, the origin. So you take your tracing paper, you cover the shape, and you mark where the main bits, the main corners of your shape are. We're going to rotate it about the origin, which is there. That means I'm going to pin my tracing paper when I do my rotation. I'm going to pin it down there so that when it turns around that point. Draw a little arrow going up your page and figure out when that turns 90 degrees clockwise. So 90 degrees is quarter of a turn, clockwise is in that direction. So when I finish my rotating, this arrow is going to be pointing in that direction. So keep an eye on it, and as soon as it's pointing where we need it to, stop your rotation, and that's where your shape is going to end. So I'm going to have a corner there, I'm going to have a corner there, one there, and the last one there. If you're doing this at home and you haven't got any tracing paper, chances are in one of your kitchen cupboards you'll have some greaseproof paper for baking, and that does the job perfectly well. Right, so pause, have a go at the next few yourself, and then come back. So this one, we're rotating. It's going through 90 degrees in an anti-clockwise direction, and it's rotating about the point -2, -1. So -2, -1 is there. There's my shape. That's going up. 90 degrees anti-clockwise is now going to turn it so that it's moving, pointing in that direction. I pin it at -2, -1. And I turn until that's pointing where I need it to be, and then trace through the shape. Just to speed it up. I'm drawing that freehand, but in an exam, for goodness sake, use a ruler. So those are rotations. So those are the 4 transformations that you need to be able to deal with, as I mentioned. So if I just go back to the front page, we can enlarge, we can translate, we can reflect, we can rotate. So what else can they throw at you? Well, they could ask you to do more than one thing. So here, first of all, they want us to reflect the triangle. Okay, so to reflect, I need to know where the mirror is. The mirror is in the x-axis. So that means that's my mirror. So this is 2 above, so it becomes 2 below. that is 6 above, so it's going to end up 6 below. So reflect, and label my answer B. Then rotate your triangle by 90 degrees clockwise about the origin. So now I'm going to take my triangle about the origin, and I need to rotate it 90 degrees clockwise. So if I put my arrow there, 90 degrees clockwise means it's going to end up pointing in that direction. I'm going to pin on the origin, swivel it round, stop, trace it over. 1, 2, 3. Label your final answer C. Okay, so 4 marks for that because they're making you do twice as much work. They could ask you to do a describing. So describe fully the transformation which maps triangle A onto triangle B. Okay, so when I'm looking at that, I can see it's been flipped. So therefore, it's reflected. So I get 1 mark for reflect. Then I need to remember that it's not enough to say it's been reflected. I need to say where the mirror is. Now the mirror is going to be exactly halfway between the original shape and its image. So I've got 1, 2, 3, 4, 5, 6 spaces between. So 1, 2, 3. So the mirror is going there. So in line equals 1. So the last thing I need to remember is that an X or a Y that's going there. It's going through the X coordinate, 1. So it's an X. So reflected, because it's clearly been flipped. Where's the mirror line? Halfway between. It's going through a 1 coordinate. Is it X1 or Y1? It's X equals 1. Describe fully the transformation which maps triangle A onto triangle B. Okay, well clearly it's changed size, so it's enlarged. So if something's been enlarged, we need the scale factor. Let's use the horizontal one. The original is 3. The enlargement is 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times as big. Then I need to know where the center of that enlargement has taken place. And this is not easy to figure out unless you do this. So what we do to find the center of enlargement is we join all the corresponding sides together. So there's the corresponding corners. So that one with that one with that one with that, and where the lines all cross is where the center is. So in this one, the center will be X coordinate always first, so it's going to be 4, 11. So 3 marks there, 1 mark for enlarged, 1 mark for the size of the enlargement, 1 mark for the center. And then the last one to look at, describe fully a single transformation that transforms triangle S onto triangle T. So I can see, hopefully you can see, it's been turned. So 1 mark for rotated. It's been turned that direction anti-clockwise through a quarter of a turn. So 90 degrees anti-clockwise. But I also need to say where it has been turned through. And if you get one as nasty as this, it's almost certainly going to be turned through the origin. But just to check, what you would do here, so there's my up the page. If I wanted to try to see if it was going to be rotated about 2-2, I pin there, turn it 90 degrees, no. So you keep trying that, but the one that I would start with every time would be about the origin. And there you go, straight away, straight onto it. So about origin, or not, if you want to put it like that. So 3 marks, 1 mark for recognizing it's a rotation, 1 mark for the turn, 90 degrees anti-clockwise, and 1 mark for the center of rotation. And that's it. So those are sort of grade C questions on transformations that doesn't take you long to revise, and should reap quite good marks.